Hey guys, what's going on? So today we are going to be talking about cohomology. We talked about homotopy, we talked about homology. Now we're going to talk about cohomology. This is where we're going to start bringing in the language of differential forms. And so with that being said, let's go ahead and get started. Make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support there. You can also support by becoming a member here on YouTube. Again, when you become a member, you get access to these videos plus more content on these videos. So in other words, if you want to see all of this video, you can become a member. Whereas if you want to see the free content, you don't have to become a member. Okay? So let's go ahead and get started. So we're turning now to the topic of cohomology. Cohomology is the crux of Chern Simons theory, or Simons theory, and will be the last point that we talk about in the topic of topology before we actually move on to the physics of Chern Simons theory itself. So if we recall the definition of our homology group, we stated that our homology group was the space of all things that could be boundaries divided out, and you divide out all the things that actually are boundaries. Okay, so what is it? This is, I don't want to go too much back into this, but the idea here is that if you have all the things that could be boundaries and you take out all the things that actually are boundaries, what you're left with are things that are sort of non-trivial boundaries. They're things that have holes in them, right? Because they're boundaries, but they are not boundaries of anything, right? So the good an analogy I like to draw here is the analogy between a bowling ball and a tennis ball, right? So a bowling ball is a sphere, a tennis ball is a sphere, but a bowling ball is filled in, right? It's got those holes in it that you put your fingers in, but those only go so deep into the bowling ball. So in some sense, it's a sphere. It's filled in. There's no holes in it. So you could theoretically, mathematically, deform the tennis ball or the bowling ball down to a point. You can do that continuously. Okay, if you're strong enough, say. However, for a tennis ball, you can't, because it's a sphere, but it's hollow on the inside, right? So in some sense, you have this thing that could be a boundary, or really it could be a boundary or something, but then when you open it up, you see there's nothing in there. It's actually not a boundary to anything. So a tennis ball, because it's hollow inside, you can't really condense it down to a point. So both objects are spheres when you just look at them, right? But your bowling ball is topologically different, mathematically different from your tennis ball, because the tennis ball, again, has kind of a two-dimensional hole in it. Okay, so that is the analogy I like to draw here between all the things that could be boundaries and all the things that actually are boundaries. The tennis ball, it could be a boundary to something, but then when you open it up and see there's nothing in there, it's not the boundary to anything. So both of them, again, they're spheres. They look like spheres, but both are topologically different from each other. Okay, with that out of the way, so the key observation here is that we found that a boundary operator, right? So we came up with this notion of a boundary operator. The boundary operator is this thing, del, and this del, when it operates on some form, say phi, it equals 0. This is a pivotal property of our boundary operator, right? This is to say that a boundary of a boundary is 0, okay? Now let's take a look at the exterior derivative. Exterior derivative behaves very similarly to the boundary operator. However, the boundary operator gives us this notion of homology, right? The space of objects that could be boundaries, space of objects that are boundaries. And what exactly is the analogy for forms, or the exterior derivative? And this is where the concept of cohomology is going to come into play. So the natural question is there a homology equivalent for differential forms? After all, they behave very similarly when we look at the similarities between the boundary operator and the exterior derivative. Okay, so we can see this mathematically. Our boundary operator takes us from our space Cn to our space Cn minus 1. So we're going one dimension lower. For our del operator, for our d operator, our exterior derivative, this takes us from n forms, a space of n forms on some manifold, to our space of n plus 1 forms at some point on some tangent space on some manifold. Tangent space at point P on a manifold. This is how that reads, right? So this is the exterior space of n forms in a tangent space at point P on manifold M. Okay? That's how we read that. So, okay. So it's going to be instructive now to talk about equivalence classes, because what's going on, what we're going to see here is that when you mod out something in some space, okay, what you actually are doing is, by the dictates of this thing, you're going to find equivalence classes in here. So let's go ahead and do that. We're going to do like a rote example here. So we're going to mod out we're going to take z, space of all integers, and we're going to mod out 4z. And the way we're going to do that is we're going to say, well, 4z is just all of the integers times 4. Right? So all of the integers, n, and then we have this 4z thing, right? And so we write that in this way, and we write that in this way, and then we get this right here. Okay, this right here is going to be, well, our space of all, so n is going to come from z here, and this n, when we distribute everything into this set, we get this, right? So n plus 0, n plus minus 4, n plus minus 8, n plus minus 12. So 4z is going to take every integer, right? So every integer n, and add 4 or subtract 4 from it. So in other words, the difference between each sequential point is going to be 4, okay? Going in the positive or the minus direction. So let's take an example. So here's our n's, our n groups. So that's coming from z. And then we're going to mod out 4z. And so for 0, this is what that looks like, and we get plus minus 4, plus minus 8, plus minus 12. For 1, 4z, well, that's going to be this set, okay? And then when we do all this addition and subtraction, we get 1 plus 0, that's 1. 1 plus 4 is 5, 1 minus 4 is minus 3, and we can do that so forth for this. We can do it for 2, 3, 4, 5, 6, and 7, and we can do it for all of the other integers, right? But I just went up to 7 for illustrative purposes, because when we look at these sets now, we see that this set here is the same as this set, right? Because we have 4, 4, 0, 0, 8, 8, negative 4, negative 4, 12, 12, and so forth. So 0 and 4, these two sets, right? These two sets are the same. They're equivalent. Then these two guys are equivalent. These two guys are equivalent, and these two guys are equivalent. This process will repeat, and essentially what we've found are 4 equivalence classes out of doing this quotient. So we could do this for the space of all real numbers, in which we would get an infinite number of equivalence classes parameterized in the interval 0 to 1, right? So for any element a in here 0 to 1 will be equivalent to any element a plus n where n is in z. So equivalently, in the example given above, where two elements A and B are in Z, are equivalent in this space here. If A minus B equals 4, or is in 4Z. More generally, we can understand this in a picture. So if we have elements A and B, that is going to be elements A and B, right? Say so 0 and 4. If the difference between them is in H, right? So 0 minus 4 minus 0 is 4, and that's in here, right? That's right here. Well, if that's the case, so if it's the case that we have this, and this, if the difference between these is this guy right here, so the difference is in here, then we have established equivalence classes. Okay, so our space big G is Z here, and H is 4Z, and so we've established equivalence classes. Okay, so now we can sort of think, well, okay, whatever BN or whatever this is, that is going to be H in this picture. Okay, we can draw equivalence classes in this space here, according to the dictates again of this space. Whatever elements are in this space, they're going to tell us what the equivalence classes are in this space. Okay. We were able to find equivalence, sort of quote-unquote equivalence classes, when we were talking about differential forms earlier. Recall that we were able to do this through looking at the dimensionality of our form spaces, right? So there was an equivalence between 0 forms and 4 forms, right? So, and then 2 forms and 3 forms, and then this automorphism, or it's sort of auto equivalence classes between 2 and 2 forms. All right, so this was sort of a way of finding. They're not really. We could sort of call them equivalence classes. There's a different name to this. We found this. We did a lot of this through Hodge duality. So Hodge duality. We talked about this before. Hodge duality and equivalence classes. These two things are different. However, the idea of finding equivalent things is something that we want to sort of keep at the forefront of our minds. These two things are different in that equivalence classes are brought about through G mod H. Hodge duality is brought about through dimensionality. Or we sort of brought it out through dimensionality of spaces. And that had to do, that fundamentally came down to, a little bit of combinatorial mathematics. But so these two things are different, but the idea of finding equivalent things to each other, we want to keep that in mind. All right. So this is not the same thing. These two things are not the same thing, but I thought that it would be useful to show that we have found sort of equivalent spaces before. I'll put quotes in here. Equivalent spaces before. In taking factor groups, we are effectively finding all of the elements in our parent space that are equivalent to each other by the dictates of the set that we're quotienting by. So the factor group, that is referring to, this is our factor group, okay? We've factored out a set of groups, if you can sort of think of it like that. So to get rid of some of the terminology really quick, what we're going to say when we start talking about cohomologies or cohomology groups is that we have closed end forms. Right, so closed end forms and exact end forms. All right. And let's now talk about an example. And this is where I think I will stop. We have a few more a few more stuff that we want to go through, and then we're going to really dive deep into cohomology in the next video, because I want to give those of you who are members an opportunity to be able to get exclusive content. All right. So again, if you don't have a membership, I've made everything just $10 as $10 per month on Patreon and here on YouTube. So if that's something that you're interested in, go ahead and make your donation. So with that being said, I'll see you guys in the next video. For those of you who are members, you can keep on watching.